As shown in this conceptual image, soft inchworm robot is suitable for self-evolution robot that can explore unknown planet. Because the mechanism of the body of the inchworm robot is quite simple, it is easy to evolve and improve them with artificial intelligence and 3D printers automatically through multiple generations, as described in previous videos. This is the sequel to those videos to explain the evolving process more in detail. This video shows the fundamental motion of the first inchworm robot, with rectangle blocks of DN gel at the bottom of its 2 legs. This robot was designed and manufactured by Mr. Minoru Takagi and Professor Riichiro Tadakuma at Yamagata University in Japan. As the linear actuator to expand and shrink the body of this inchworm robot, 2 lead screws were used at its front and back parts. The metallic plate at the bottom of the inchworm robot works as the cathode of the electrical circuit to activate the DN gel. When one leg works as the lifted leg with the current flow and water that emerges around the cathode plate under the lifted leg reduces the frictional resistance, lead screws works in orchestrated way to move the lifted leg to the target direction. After moving the lifted leg, the current on that leg stops, and the water vaporizes from the cathode plate at its bottom, so the frictional resistance of the leg is also recovered. Now this leg can be used as a supporting leg with large enough frictional resistance. After that, the other leg works as the lifted leg with the current flow on its DN gel to reduce its frictional resistance. By repeating this process multiple times, this inchworm robot can continue to move forward smoothly on the metallic plate as the cathode. To realize the flexible inchworm robot to move in narrow space, shape memory alloys were adapted as the linear actuators instead of lead screws used for the first prototype of the inchworm robot. By using shape memory alloys to expand and shrink the body of the inchworm robot, its flexibility can be much improved, and its total size and weight can be also reduced. This improvement is suitable to adapt the inchworm robot to narrow environments such as pipes and drains. These images show the body mechanism of the second prototype of the inchworm robot that uses shape memory alloys to expand and shrink its body structure. Bended metallic plates are used as electrodes for double network gel, DN gel. The bellows structure was adapted to the segments of the inchworm robot to follow linear motions of the shape memory alloys smoothly. This is the motion of the second prototype of the soft inchworm robot with 2 segments. By switching the lifted leg and the supporting leg with current flow, the robot can move forward smoothly in a narrow pipe. Because the anode and the cathode was deployed on the leg together, the metallic plate at the bottom of the first prototype of the inchworm robot was not needed this time. The double network gel used for this soft inchworm robot had rectangle shape. These images show the body mechanism of the third prototype of the inchworm robot that uses shape memory alloys to expand and shrink its body structure. Metallic strings work as electrodes for double network gel, DN gel, and hold the DN gel tightly. The similar bellows structure to the second prototype was adapted to the segments of the inchworm robot. This is the motion of the third prototype of the soft inchworm robot with 2 segments. By switching the lifted leg and the supporting leg with current flow, the robot can move forward smoothly in a narrow pipe. The double network gel block used for this third inchworm robot had more sophisticated structure than the second prototype. The tip of the double network gel block was tapered to restrict the width of its contact area with ground. With this improvement, the effect of the water from the double network gel block was enhanced to control the frictional resistance between the robot's feet and ground. The latter soft inchworm robots also had the similar shapes of the double network gel blocks for better control of the frictional resistance. These images show the body mechanism of the fourth prototype of the inchworm robot that uses shape memory alloys to expand and shrink its body structure. Metallic plates are used as electrodes for DN gel. These electrodes are attached to a rectangle polymer frame fabricated with a 3D printer. The spiral spring structure was adapted to the segment of the inchworm robot to follow linear motions of the shape memory alloys more smoothly than bellows structure of the third prototype of the inchworm robot. This fourth prototype of the inchworm robot was developed by Mr. Moses Gladson at Yamagata University in Japan. This is the motion of the fourth prototype of the soft inchworm robot. By switching the lifted leg and the supporting leg with current flow, the robot can move forward smoothly in a narrow pipe. These images show the body mechanism of the fifth prototype of the inchworm robot that uses shape memory alloys to expand and shrink its body structure. The rectangle spiral spring structure was adapted to the segment of the inchworm robot. This fifth prototype of the inchworm robot was also developed by Mr. Moses Gladson at Yamagata University in Japan. This is the fifth prototype of the soft inchworm robot with two segments. Its body is also composed of DN gels, shape memory alloys, and electrodes. With only these components, this robot can move forward and backward in the plane with the physical principle described before. 3 DN gels are attached to the body of the inchworm robot and work as its legs this time. This is the motion of the fifth prototype of the soft inchworm robot. By switching the lifted leg and the supporting leg with current flow, the robot can move forward smoothly. In the future, flexible omnidirectional driving gears with various curvatures can be adapted to the soft inchworm robot instead of shape memory alloys. The omnidirectional driving gears corresponding to freeform surfaces can provide larger force than shape memory alloy and activate the soft inchworm robots in harsher environment more effectively and smoothly.